linear second order ordinary differential equations. So linear second order ordinary differential equations. So we are now starting linear second order ordinary differential equations, and we start with the type 1. This takes the form So in our type 1, this takes this particular format. A d squared y dx squared plus b dy dx plus cy is equal to 0, where A, B, and C are constants. Where A, B, and C are constants. Where A, B, and C are constants. If A is equal to 0, then the dE reduces to B dy dx plus cy is equals to 0. It will reduce to a first order differential equation which can be solved by separating the variables. That is, now this implies what? If we are to solve this, this will give us b dy dx is equals to minus cy, which implies dy all over y will be equal to minus c all over b multiplying dx here. We have separated the variables. Since c and b are just constant, they can be on any side, and we have let them to be on the side of dx. So this side represents x values. This other side represents the y values. So the integral of dy all over y will be equal to the integral of minus c all over b dx. Which gives us, when we integrate that, implies what? Ln of y will be equal to minus c all over b x plus maybe a constant k plus maybe a constant k. That's constant of integration. So this will now be, y will now be equal to e. If you make y the subject here, e power minus C all over Bx plus K, which will be equal to, according to laws of indices, e power minus C all over Bx multiplying e power K. Now, K is a constant, and n exponential is also a constant. So e power K can be replaced by another value, which can be replaced by another constant, which we can call A, e power minus C all over B multiplying x. So y is equals to that. Now, if y is equals to that, we can, minus C all over B is just another constant. We can give it another name. So if we let minus C all over B to be equal to a constant m, therefore our y is equals to AE power mx is a solution. It's a solution to the dE, if A is equal to 0. Now, what about when A is not 0? And y now takes that format. Now, we substitute the value of y into this equation, into our equation that was stated as our type 1. As our type 1. So we say substituting for y in the equation. In the equation, it will be a d squared x a e m x plus b d dx, or that is squared a e m x plus c into a e m x. This is what is equal to 0. Now, when we differentiate the way we are saying here, second derivative of this, we'll now have a with a capital A, with a capital A, m squared e power mx plus b with capital A m e power mx plus a plus c a e power mx. This is what is equal to 0. We can see a e power mx is common in all, is common in this expression. So we factorize it out. So this will give us a m squared plus bm plus c, and this one is equal to 0. But we know AEMX cannot be equal to 0. Since this A that we have here, A was e power k, and any exponential raised to any power cannot be a 0. And A power mx is equal to 0. If the value is definite, then we cannot get a 0. So this implies only am squared plus bm plus c is equal, can be equal to 0. That is the only portion that can bring this expression being equal to 0. Now, this equation, if we call it equation 2, We say equation 2 is known as equation 2 is known as the characteristic equation. Characteristic equation or the auxiliary quadratic equation of the differential equation of the differential equation. Solution of the auxiliary of the AQE, solution of the AQE, the auxiliary quadratic equation will result into various values of M, into various values of M. That is M1 and M2. M1 and M2. With the values of M1 and M2 known, we can be able now to give a solution to our differential equation if M1 and M2 are known. So, we say not carefully, we say case 1. If b squared is greater than 4ac, the solution the roots of the AQE will be real and unequal. Will be real and unequal. That is, will be real and equal and unequal. That is M1 and M2. Therefore, the solution to the DE, is given by y is equals to AE power M1x plus another constant arbitrary b, A power M2x, where A and B are arbitrary constant. Capital A and B are arbitrary constants. Case 2. If b squared is equal to 4ac, the roots of the AQE will be real, and equal to each other, That is, M1 will be equal to M2, which will be equal to just a mere M. Therefore, the solution to the DE, the solution to the DE takes the form y is equals to, takes the form y is equals to a power mx into ax plus b into ax plus b. Case 3. B squared is equals to, b squared is less than 4ac. Then the roots of the AQA will be complex, in the form m is equals to, will be complex, m is equals to alpha plus or minus j beta. Therefore, the solution to the DE takes the form y equals to a power alpha x into a cos beta x plus b sine beta x Now, example 1 here. So, can proceed. So example 1, solve the d squared y dx squared minus 11 dy dx plus 7y is equal to 0. Plus 7y is equals to 0. So in our solution, we are going to write it where we are going to say represent let d be equal to d dx and d squared to be equal to d squared dx squared. So this implies what? 4d squared y minus 11 dy plus 7y is equals to 0, which implies y is common. We can say 4d squared minus 11d plus 7 into y is equals to 0. Now, whatever is in this bracket, this is where we are going to derive our auxiliary quadratic equation. By inserting where we see a d, we input an m. So the auxiliary quadratic equation will be found this way. We say this is 4. That will now be replaced. D squared is being replaced by m, so it will be m squared. 11m plus 7 is equals to 0. Now we want to solve this. Solution for this, you can use formula method, or you can use any method of solving quadratic equation that you know on this earth. That is, we can solve by formula method. M will be equal to 11 plus or minus root of, using formula method, that is 121. 11 squared is 121 minus 4 times A, which is 4, times C, which is 7. All over 2A, 2 times 4, which gives us 11 plus or minus 11 plus or minus 3 all over 8, which gives us 14 all over 8, or 8 all over 8, which is equals to 7 all over 4, or 1. 7 all over 4, or 1. So, therefore, the solution to the D is given by y being equals to arbitrary constant A multiplying E power m1 x plus B e power m2 x, which is now equal to A e power 7 all over 4x plus B e power 1x. And that is the solution to the differential equation given in example 1. Solve the DE. 25d squared x dt squared plus 10d dx dt plus x is equal to 0. So in our solution, we can say this can be written as 25d squared plus 10d plus 1. All this multiplying x. This is what gives us a 0. So we say now, from here we prepare the auxiliary quadratic equation, or CE, characteristic equation. And that is 25m squared plus 10m plus 1 is equals to 0. M will be equal to minus 10 plus or root of b squared. 10 squared is 100 minus 4 times 25 times 1. All over 2 times 25, which is 2 times 25 is 50. So here we have 50, which gives us minus 10 plus 0 over 50, or minus 10 minus 0 all over 50, which is equals to minus 1 all over 5, or minus 1 all over 5. So it is equal to minus 1 over 5, or carrying twice. Therefore, the solution to the DE, is given by we were solving for x. Here we are not solving for y, because the x dt, x is a function of t. So we are solving for x. X will be equal to e power, what was here? M, our m is 1, negative 1 over 5. But now multiplying t. Now we have here AT plus B, not now X, because X is a function of T. Here we don't have Y as a function of X. So this becomes the solution to that differential equation. Now we can move to example 3. We can now move to example 3. Yeah, now we are having solved the d squared x dt squared plus 6dx dt plus 34x is equal to 0. This is also a second order, first type that we are having. So we say in our solution, we can rewrite the d in this format and say d squared plus 6d plus 34. That is 6d plus 34. The whole of this multiplying x, and this one is equal to 0. This one is equal to 0. We can now prepare the AQE, which will be m squared plus 6m plus 34 being equal to 0. We can solve this by formula method. M will be equal to minus 6 plus or minus root of our b squared will be 36 minus 4 times a1 times c 34 all over 2a 2 times 1, which will be equal to minus 6 plus or minus root of negative 100 all over 2, which will be equal to minus 6 plus or minus root of 100 is 5, and root of negative 1 is a j5. Root of negative 100 is 10, and root of negative 1 is j, so it is j10 all over 2, which will be equal to a minus 3 plus or minus j5. We say m is equals to minus 3 plus or minus j5, which is equivalent to alpha plus or minus j beta. Now we can show this with an arrow so that we pick our values. We show this. So this implies what? Our alpha is negative 3. Our alpha is negative 3 and beta. And beta is equals to 5. And beta is equals to 5. Therefore, the solution to the DE is given by x is equals to e power minus 3t into a cos beta t, and our beta is 5, cos 5t, plus b sine beta t, and our beta is 5, sine 5t. And that is the solution to the said differential equation. So in our example 4, we say solve the d for d squared r d theta squared plus 8 dr d theta is equal to 0. So in our solution, this one can be written as, this can be written as 4d squared plus 8d plus 8d. This one multiplying plus 8d, this one multiplying theta, and this one is equal to 0. Our theta cannot be 0 because that's, just a minute. Multiplying r, not theta, multiplying r. Our r cannot be 0 because that's what we are trying to solve for. So we develop here auxiliary quadratic equation. Auxiliary quadratic equation will be given by 4m squared plus 8m is equals to 0. This implies what? 4m, we can do this by factorization. 4m into m plus 2 is equals to 0. So solving here we get, from here m is equals to 0, or m is equals to negative 2, or m is equals to negative 2. Therefore, the solution to the DE, is given by R being equal to, these are two real rules which are different from each other. It is AE power 0 theta plus BE power negative 2 theta. Zero times theta is 0. E power 0 is 1. So the solution, that is, our R now will be equal to, A plus B exponential negative 2 theta. And that is the solution to that differential equation. That's the solution to that differential equation. So in our type 2, we are now having a linear second order differential equation, which takes this format, where we are not now equating to 0, we are equating to another function of x. Now, this particular statement can be written this way. When there is f of x here, we also have a 0. What brings a 0 will be a solution to the same. So we say y seems to be in two parts. One is known as yc, one is known as yp, where yc is the complementary function of y, and yp is the particular integral of y. So when we substitute, when we add yc to yp to generate a y, we are now substituting where there was y, we put yc plus yp, yc plus yp, yc plus yp. And in solving, when equating to 0 plus function of x, the part that brings in a 0, it is a part of the complementary function of y. A part that brings function of x, yeah, this one should be function of x. A part that brings a function of x, is the particular integral. So the complementary function will only lead us to something which is equated to 0. And the particular integral will lead us to what it is equated to function of x. Solving any differential equation which is equated to 0 is what we have just finished in our type 1. So solution of part 2, equation 2, is not a problem by now. What we don't know by this particular instant is the solution, how to solve for particular integral. Let's just put here yc is equal to complementary function of y. That is, can also be written as CF or IP particular integral you can now be written as PI. And now be written as PI. Now, I would like now to see various methods of solving for the particular integral. Various methods for solving for the particular integral. There are so many methods of solving. There are so many methods for solving particular integral from a differential equation. And here we'll only be solving using the method of undetermined coefficients and the operator method. So the following methods. So we said the following method are to be used for the solution of the particular integral. Method of undetermined coefficients, part 2, the operator method. Method of undetermined coefficients involves a way where we are going just to let for our particular integral. We are going to assume a particular integral takes a certain format, and this will be guided by the way our function of x is given, what appears on the right-hand side of our differential equation. If our function of x is a polynomial, what we need to check is only the highest power we have in that particular expression. For this highest power, in our letting, we'll start from k1 multiplying x power 0. Up to a term, we have a constant multiplying the highest power included in our function of x. Like in this format, because we are ending at x cubed, our letting will be k1 plus k2x plus k3x squared plus k4x cubed. That is, we only check the highest power when we are dealing with a polynomial. Even if there was only one term multiplying x cubed, the letting will be the same as this. So we only check only at the highest power. In our number 2, if our function of x is equals to a constant multiplying an exponential, px, where p is a constant, then we let our yp to be equal to another arbitrary constant k, not this c. C is now different from the k. This one becomes arbitrary, but we maintain exponential px. If the CF doesn't contain the term ae power px or be power px, otherwise, the letting for yp should be multiplied by x so that we deviate from what is already contained in our complementary function. After deviating, if it is now different from what we have in our complementary function, we proceed and process for our particular integral. But if it is still containing a term like that, then we deviate it further by multiplying also by another x. That is it. We go now to number 3. Number 3, we say if f of x is equals to so in our number 3, if f of x is equal to c1 cos px and or c2 sin px, you can have a case where f of x is just a constant multiplying cos px or a constant multiplying sin px. Or it can be this, you add it to this. Then the letting is the same. It will be k1 cos px, we maintain the cos, we maintain the p here, plus k2 sin px, we maintain that p. We don't change. What changes? We don't include the c1, we don't include also maybe if there is c2, we don't include them, we only include k1 and k2. We use k1 and k2 arbitrary constant, not the constant that we have in our right-hand side of the differential equation. If the CF doesn't contain a cos px or b sin px, appearing alone, that is when we do that letting. Otherwise, if any of these appears in our complementary function, then the normal letting, what we would use for the letting for yp, we may deviate from that particular expression by multiplying each and every term here by x. So we say otherwise the letting for yp should be multiplied by x, so that we make it different from whatever is already contained in our complementary function. Our next meeting now will be having examples towards the same. We will have examples where we will be having polynomials, we will be having exponential, and we will be having also trigonometric terms, and then solve them, see the method, how they are being solved. So that's the end of our today's learning, the introduction to type 2, how it is done, and how we use the method of an undetermined coefficient.